Hello, my name is Bryce Jensen, and I'd like to introduce a comparative study of participants in a NASA robotics competition and a proposed approach. The NASA robotics competition is a competition to design, build, and test a robot capable of mining simulated lunar soil or regolith for later ISRU for the larger Artemis program. Sonoma State University is competing in this year's RMC for the first time in university history. To begin, our team performed a multidimensional trade survey of the 2019 competition year. Nearly 30 teams were analyzed and evaluated on various mission performance-based criteria. Some of the factors considered were events such as the robot getting stuck or having a mechanical problem, or things like how much regolith was deposited, and more. And as you can see, the 2019 robots came in a wide range of forms. From our trade study came two main discussions, the first being tracks versus wheels. Tracks seem good on paper because they have low ground pressure. However, the implementation can be complicated and introduces additional mass in an already mass-constrained system. And some tracked robots got stuck, proving that tracks are not necessarily a magic bullet solution. Wheels can be made to work, but they have to be large enough to have low ground pressure. Most teams chose wheel designs, and we did as well. Our second discussion is on mining tools, and we found that four main types of mining tools were typically used, these being scoop arms, bucket wheels, screws, and conveyor belts. Our design goals and some of our constraints are listed below. We decided for high levels of modularity and open software for maximum customizability and future reuse. From our trade study, we selected two main features, the first being wheels. For these, we decided a large radius and wide track would be the best thing to give us a low ground pressure. And grousers were added to increase our traction in loosely packed regolith. From our trade study, we also decided on independently driven wheels for maximum mobility. Our bucket wheel excavator comes from the idea of the terrestrial bucket wheel excavator, which has proven to be highly effective and is promising in low-gravity ones. We mounted the bucket wheel on a movable stage for a plunging type motion. We gave it a hubless design for extra tool cut depth. Integrating these two systems using Fusion 360 gives us our approach shown here, where we have the main tool mounted in the center of the robot, mounted on two linear actuators to drive that wheel up and down into the regolith below. Our system functional block diagram is shown here, where we have the control station with a video display and our interface talking over an Ethernet link over Wi-Fi to our companion computer running on the robot. That companion computer will be running our mobility, mining, and dumping systems, as well as cameras. It will also stream that camera data back over the Wi-Fi link to the control station to complete our telerobotic control. For future work, we propose a real-time object detection using machine learning system. For this, we need to develop an all-in-one, bolt-on style module that we can apply machine learning to new platforms. We need to develop a trainable module that can be adjusted for new mission parameters. So the all-in-one bolted module can be applied to multiple platforms, be they optionally crewed or telerobotic uncrewed vehicles. Thank you.